Welcome. We're going to talk about the strength of the lithosphere in this presentation, and this has got to do with rheology, which was a topic that I was first introduced to many years after I started teaching tectonics, when I offered this class at Stanford while I was on sabbatical. And the professor I was offering it with, Simon Klemperer, said, you need to add, we need to add rheology. So of course we did. And so that's what we're going to talk about, rheology. And let's watch a video so you'll get some ideas. It's a complicated topic, but an interesting one.
Tech now works. Engineering the better way. Stress-strain curve is a stepping stone to understand properties of engineering materials. This curve is plotted for variety of engineering material during tensile test. In this video I will explain the stress and strain curve in very easy way. So, let's start with basic terms we have used in this curve, which are stress and strain. In tensile test, stress is calculated as load applied to a material, divided by the cross-sectional area of the material. The strain is the deformation or displacement of material due to applied load and can be calculated as change in length divided by original length. In stress-strain curve, the stress is shown along the y-axis, and strain is shown along the x-axis. As we load the testing object in tensile test, it begins to deform and stress continues to raise linearly up to a point A, on this graph. At this point A, if we remove the applied load on the testing object, it will restore to original shape without any deformation. As you can see in this graph, from point O to A, the stress and strain has a linear relationship, and stress is directly proportional to the strain within this region. Beyond point A, the proportionality between stress and strain no longer exists, hence the stress at point A is called the proportional limit. The Hooke's law is valid up to this point only. The slope of this line OA represents the Young's modulus, also known as modulus of elasticity, and it can be calculated as stress divided by strain within proportional limits. Higher slope means stiffer and stronger material, for example high carbon steel, and its curve will look like this. Whereas for flexible material like elastomers, curve will look like this. Remember, these curves are not to scale. With increase in stress beyond the proportional limit, strain being to increase more rapidly for each increment in stress. From point B to C, there is considerable increase in strain without much increase in stress. This is because of plastic deformation in the metal. And this phenomenon is known as yielding. The point B, where this yielding begins, is known as the yield point, and the corresponding stress value is known as yield strength of the material. When the metal is strained beyond the yield point in the region BC, the material experiences a change in its crystalline structure and apparently becomes stronger and more difficult to deform. Thus, an increasing stress is required to produce additional plastic deformation beyond point C. This phenomenon is known as strain hardening. The load eventually reaches its maximum value and corresponding stress at point D is known as ultimate strength or ultimate tensile strength. Further stretching the testing bar, beyond point D, leads to decrease in cross-sectional area of the bar. And it can be seen here. This localized reduction in area is termed as necking. Due to reduction in the cross-sectional area of the bar, load-bearing capacity of the bar reduces drastically, and the curve starts dropping beyond point D. Eventually a point E has reached where testing bar fails. The stress at this point E is known as breaking strength of the material. This curve is known as engineering stress and strain curve, because the stress and strain calculated are not true. The stress calculated based on the original area before the load is applied. In reality, as the load is applied, the area reduces so that the actual or true stress is larger than the engineering stress. And true stress and strain curve will look like this. Hope you really enjoyed this video. Please subscribe my channel for more engineering fundamentals. And don't forget to press bell icon. Thank you.
I hope that that video was a lot to digest, but let's take the concepts that were developed in there and simplify them and use them on rocks. So here we have the diagram, the stress strain diagram, and stress on the y-axis and strain on the horizontal axis. And as I said, it's quite confusing because when I came to UTD in the early 80s, I thought stress and strain were the same thing, as many of you may very well, but they're quite different. Stress is the force applied per unit area, and strain is what happens to, in this case, the rocks. So we talked about, the video talked about the elastic deformation, and elastic means, as you well know, if you pull on your underpants lining and let it go, you can snap it. We all did that at least boys did in high school to other people. But that's it. So if you apply a stress up to a limit, the elastic limit, and then release that stress, the rock will go back to its original configuration. But if you apply more stress than the elastic limit, the rock will strain in ways that cannot be recovered by removing the stress, and that will in fact show more strain per increment of stress. And here we see the difference between what we call elastic deformation and ductile deformation. And this diagram is showing, okay, we're going to stress a rock beyond its elastic limit, and then we're going to release that stress, and the rock will relax, but it won't go back to its original configuration, and this is called permanent strain, right? So strain describes the deformation of a rock due to applied stress. And when a rock is subjected to increasing stress, it passes through three stages of deformation, strain in succession: elastic deformation, ductile deformation, and fracture. Fracture is when the limits of both the elastic and the ductile deformation are exceeded. A lot to digest, so don't hesitate to ask questions if we got them. So one of the most important considerations is what we call confining stress, which is also isotropic stress. So this is a uniform squeezing of a rock owing to the weight of the overlying strata. So here we've got sigma, which in this case refers to stress, and that's equal to density times gravity times the thickness of what of it is overlying the material of interest. And we can talk about hydrostatic stress or hydrostatic pressure, same thing, or lithostatic stress or pressure. Now, hydrostatic, it is the stress due to the weight of the overlying water. So that's 1 atmosphere for 10 meters. So when we were diving at 6,500 meters in the Mariana Trench, the hydrostatic pressure was 650 atmospheres. Lithostatic pressure, because the weight of rocks is greater than the weight of water, is about 3 times greater. So in general, and we see that it's on the order of 3 atmospheres for 10 meters. So that works out to 1 gigapascals for 33 kilometers in the lithosphere. So the crust is typically 40 kilometers thick. So the pressures, the lithostatic pressures we expect at the base of the crust are a little bit over 1 gigapascal. Okay, so a couple of things. High confining stress hinders the formation of fractures and so increases the strength of the rocks. And we see that on this diagram. These are all kinds of rocks, from limestone, sandstone, greywackies, granites, all sorts of things. And that's the stress in megapascals, right? There's 10 megapascals in a gigapascal. I'm sorry, 1,000 megapascals in a gigapascal. And this is the normal stress in megapascals. So that's maximum. This is normal. It's basically a 1-to-1 relationship. The maximum stress is equal to basically the overall stress. And these are measurements in the laboratory And they fit a curve, which is this R is equal to about 0.85. Okay. So what you can see is that overall, other things being equal, rocks at depth are stronger than rocks at the surface. Now, this is a very interesting result and one that causes a lot of problems for plate tectonics. And the reason for that is if you think about the plates moving, something has to be giving. And if the deeper you go in the earth, the stronger the rocks get, then how can anything move? Nothing at the surface can easily flow and move. So something else is going on, and we're going to talk about that. All right, so this is known as Byerly's law, this relationship between the normal stress, the coefficient of friction, and the brittle shear strength. So this is something very important to people working in the oil field because they have to, in order to frack the rocks, they have to overcome the strength of the rocks. All right, but what if the stress is not isotropic? And it does, raise your hand if you're not sure what isotropic is, so I know whether or not I need to go down this road. 1001, 1002, 1003. Okay, I'm assuming everybody knows what isotropic means. So what if the stress is not isotropic? Then we can describe using the stresses in three directions. So sigma 1 is the highest stress and sigma 3 is the lowest stress, and we can talk about the orientation of the stress axes. Sigma 1 is the principal compressive stress, and sigma 3 is the minimum compressive stress. So horizontal sigma 1, that is compression. Makes sense. You're pushing sort of horizontally. If sigma 1 is vertical, that is extension, right? Okay. All right, so here we're looking at some things that look like maybe geologic structures. Here we've got at the top some folding. So you can see where sigma 1 is. Sigma 1 there is horizontal. In the middle, we see extension, tension. Sigma 1 there is vertical. It's the least compressive stress is actually negative, and that is horizontal. And then we can talk about shearing as a different orientation of the stress axes. Any questions about the stress axes? A lot of this was, I'm sure, covered in your structural geology class. Okay, now Walter talked last week about the orientation of the maximum compressive stress. So the length and the width of the lines indicate the degree that the axis is horizontal. A vertical sigma 1 is a dot. So the red color indicates recent events, which are earthquakes. All right, now there's a thing in the oil industry called borehole breakouts. These reveal the orientation of the principal stress axis, right? So borehole breakouts are enlargements and elongation of a borehole formed by spalling of fragments in a direction parallel to the minimum horizontal stress, right? So here's borehole breakouts on either side. This would be the minimum. This would be sigma 3. So that means sigma 1, which is always perpendicular to sigma 3, would be oriented like that. So these are borehole orientations of borehole breakouts. And can be used to understand the orientation of the principal stress axis in the crust. So now rock compression tests. When you compress a rock, eventually it will fail and fracture. These orientations give you information about the orientation of the stress axis. And this goes back a long time ago. This is 80 years ago. And here you can see the orientation of sigma 1, sigma 2, and sigma 3 in different orientations. Here we're looking at sigma 1 vertically. Remember, that's going to be extensional. That's what we're seeing here. Here we have sigma 1 horizontal. That's going to be compressional. These are like little thrust faults. And this is sigma 1 horizontal, but in the same plane with sigma 3. That gives us a strike slip system. Okay. Let's watch another video. We love videos. Now let's talk a little bit about brittle versus ductile deformation. So just very simply, brittle substances break, ductile substances flow. And when I used to teach tectonics in person, we would bring some silly putty and students could see that the same substance under different strain rates would either behave brittly or ductilely, right? If you pull on the silly putty continuously, it will stretch, it will deform ductily. And if you slam it down, it will fracture. That's a strain rate. So brittle substances break, ductile substances flow, and all materials can be brittle in some conditions, ductile in others. All solids are brittle under certain conditions, ductile under other conditions, which I just said. The higher the temperature, the more ductile and the less brittle a solid becomes. Now, this is going to be key for understanding how plate tectonics is possible. Rocks are brittle at the surface and become ductile at depth where they are hotter. And this is one of the challenges for geologists is we live on the surface. So we understand rocks under brittle conditions, but rocks are brought up from depth, and sometimes we have to imagine or understand how they behaved and the way they formed. So these diagrams here on the right are showing you two examples. One is of a brittle rock, which has very little ductile deformation prior to fracture, right? The elastic limits are the same, that's Z. And then with the brittle rock, it only can take a little bit of strain before it breaks. And the lower one can take a lot of stress before it breaks. It can accommodate a lot of strain before it breaks. Now so we looked at a video of the brittle deformation of peridotite. Let's look at one of the ductile deformation. Right. So ductility. Ductility is the ability of an object to be drawn into thin wires without losing strength. That's an engineering description. but obviously there's elements of that definition that can be used for rocks. So rocks are more ductile when they're hot, when there are high confining stresses, and these are both characteristics of the deeper crust and mantle, and under low strain rates. Now, in addition, the presence of water, which can be incorporated into mineral structures, that also enhances the ductility of rocks by weakening the chemical bonds and forming thin films around mineral grains. And there are differences in the relative ductility of minerals. Quartz, garnet, and olivine are relatively brittle, whereas mica, clay, calcite, and salt are relatively ductile. And we know this intuitively. You know, micas are these sheets, and you can imagine these will deform very nicely. So how can solids flow? Which is another way of answering Wegener's question, you know, or his critics' questions of how is it possible for the continents to move? And this is called creep. And this is a concept from material science, where creep is the tendency of a solid to move slowly or deform permanently under the influence of persistent mechanical stress. Flow is away from the principal stress axis and towards the minimum stress axis. Creep is more severe in materials that are heated for long periods and generally increases as solids meet near their melting point. So again, geologists have strong intuition about natural materials at the surface, which are at 25 degrees centigrade or so, nowhere near the melting temperature of rocks. But as rocks or any material approaches their melting temperature, they lose strength. So there's two main mechanisms for creep. There is dislocation creep and there is diffusion creep. And these are confusing terms, but we'll talk about them. Dislocation creep is more important at high strain rates. Diffusion creep is more important at high temperatures. So these concepts of creep, ductile deformation, and viscosity of solids are intimately related. So let's talk about dislocation creep. So dislocation creep is involves the movement of dislocations through the crystal lattice, in contrast to diffusion creep, in which the diffusion of vacancies is the dominant mechanism. So dislocation creep causes plastic deformation of individual materials. So here's, you can see here in this diagram, there's a dislocation, right? These atoms are lined up, or these unit cells are lined up, and then there's a little problem there. And then with under strain, then that dislocation will migrate in the direction. That's one way that the crystal can deform ductily. Diffusion creep refers to the deformation of crystalline solids by the slow movement of atoms and vacancies through the lattice. And this takes place at high, what they call homologous temperatures. We don't have to get into the definition of that, but basically the homologous temperature is a fraction of the melting temperature of the solid, right? And different solids melt at different temperatures, so they have different homologous temperatures. All right, so let's get on to rock strength. So rock strength is determined by the strength of the weakest abundant mineral. So quartz, continental crust is quartz rich. So the properties of quartz are important for the strength of continental crust. On the right, we see a plot of rock strength versus depth. And you'll see a number of things you're familiar with here. One is the moho, base of the crust. And so you see one strength profile for the crust, and then below it is the mantle. And you see a different strength profile for the crust. And then below that is the lithosphere-asthenosphere boundary, which we've talked about before. So let's talk first about rock strength increasing with depth. So we've talked, when we were talking about Byerly's law we were talking about the fact that rocks get stronger as the confining pressure increases, right? Linearly. So this part of the curve, this linear part of the curve is following Byerlee's law. And for that matter, this part of the curve down here in the mantle. So rocks shallower than about 15 kilometers, they're strong, which means they're going to fracture. There's going to be brittle deformation if they fail. But because temperature increases with depth, the weakest mineral in the continental crust, which is quartz, that becomes progressively weaker, and it is the weakest mineral that determines the strength of the rock. So, as long as Byerlee's law is determining the strength of the rock, it will continue to increase with depth. But as soon as the temperature dependence of a mineral, and the weakest mineral is quartz, becomes important, then it's going to be temperature that controls the strength of the rock. And that's why you get this funny curve.
I'm curious, it's referring to quartz being the weakest. Does it mean the most brittle?
No, in this case, so the rocks are the actual mineral that a rock is composed of doesn't matter as long as we're dealing with Byerlee's law, as long as it's the confining pressure that's determining rock strength. But as temperature increases with depth, then the least strong mineral under those conditions is determining the strength of the rock. And that for continental crust is quartz.
Hey,
I was thinking being a 7 on Mohs hardness, maybe it's just because of its silica content.
Mohs hardness is a good example of brittle strength, not ductile strength. You're doing Mohs hardness tests at atmospheric temperature, nowhere near the temperature of melting of quartz. Yes, Clint.
does this have to do with quartz having the lowest melting temperature, so
Yes.
the homologous
Yes.
temperature would be lowest?
Yes, exactly. Good point. This is confusing. I'm glad you guys are asking questions, because if you're not confused, then you're not paying attention. All right, so we're seeing here the strength of the continental crust as a function of depth, right? Following Byerlee's law down to some point, and then following basically what's controlling the creep, whether it's diffusion creep or dislocation creep in quartz at greater depth. Now, you might be puzzled. Why do we see the Byerlee's law curve show up in the mantle? Because olivine is stronger than quartz. So olivine melts at a much higher temperature than quartz. So you're going to get a much higher homologous temperature for olivine. So you'll get something like this, right? So strong in the crust, weak in the lower crust, strong in the upper mantle, and getting weaker with depth, because it's getting hotter and hotter as you go down until there's no strength whatsoever at the lithosphere-asthenosphere boundary. That's one way to look at the difference between lithosphere and asthenosphere. And as you may recall, I have stressed several times that we're dealing with yes, that the asthenosphere has no strength, which allows the lithosphere to flow over it. Here you're seeing a mechanical expression of that by looking at the strength. So at 1300 degrees, the asthenosphere, the rock strength is incredibly low. Brittle deformation is no longer possible. The final disappearance of all brittle deformation properties marks the lithosphere-asthenosphere boundary. Now, what we're looking at here is a jelly sandwich. And you're going to go, what? That doesn't look like a jelly sandwich to me. But think about it. Strong, weak, strong. Bread is strong. Jelly is weak. Peanut butter is a little bit stronger, but So this is kind of a jelly sandwich, a mechanical structure. I like the analogy with jelly sandwich because we all have a feel for jelly sandwiches. Other people call this a Christmas tree, which refers to the sort of the shape of it. But the jelly sandwich really calls to mind what we know about strength. I mean, there's another favorite food of students that might also be a useful analogy, and that's Oreos. You know, the cookie part, the biscuit part on the top and bottom is the strong part of the Oreo cookie, and if you want to, you can make the upper and lower slide over it because the filling is so weak. All right, so now we're getting into rheology. Now I hope you're starting to understand what we're talking about when we use the word rheology. Rheology is the study of flow in matter. So it's from the word rheos, which is stream or flow, and the suffix ology, the study of. And so people go, wait, solids can't flow. Well, can solids flow? Is ice a solid? Can it flow? Yes, I don't think anybody would doubt that. What about salt? Can salt flow? Salt's a solid. Yes, here is a structure in a Louisiana salt dome. That's clear. Those layers were originally horizontal, and now they are definitely not horizontal. And then we can talk about other kinds of rocks. Here we have a marble and gneiss, and that is clear evidence of flowage. Somehow that layering was originally horizontal and has since been completely transposed, and it's showing flow. So we know at one level that solids can flow, but our intuition tells us that they can't. But for sure it can, and this is the world of rheology. Very interesting world. So the style of deformation varies with rock strength and thus temperature. So here we're going down into the earth, 100, 200, 800 degrees. So we're going down, and this is the strength. And here we see Byerle's law being followed. And here we see the realm of creep, diffusion and dislocation creep. One curve being controlled by quartz, the other one, feldspar, is clearly a stronger rock, melts at a higher temperature. And so these are the nature of faults that we might see as a different depth. Though near the surface, these faults are very sharp features, very clear fractures. And as you go deeper and deeper, you get more and more ductile fabrics in them. And it becomes the same amount of displacement across the surface will result in very different manifestations. So let's talk about strain rate. We talked about strain, which is the deformation of rocks, but that can happen at different rates. The strain rate is the rate of change in the shape or volume of a material with respect to time. So strain rate is strictly equivalent to the deformation rate. Strain is basically the ratio of two lengths, which is a dimensionless quantity, that is a number with no units. Therefore, strain rate is given in units of per time. So SI units, the strain rate is given in per second. So which is the larger strain rate, 10 to the minus 3 per second or 10 to the minus 6 per second? 10 to the minus 3 per second is a 1,000 times faster strain rate than 10 to the minus 6 per second. What is the approximate strain rate of an automobile accident? Well, this is obviously depends on the kind of accident, but let's imagine it's a front end collision. That would be a 10% change in shape of a automobile, and so that would be almost instantaneous. So it'd be something like 10 to the minus 1 per second. Very, very high strain rate. So geologic strain rates are, as you can imagine, much closer to 10 to the minus 6, except perhaps instantaneously during an earthquake when they're going to be much higher. So just, and you won't have to do these calculations on the midterm, but it is useful to have been familiar with them. Just so you know, there's about pi times 10 to the 7 seconds per year. Hence, a strain rate of 100% in 1 million years would be 1 per millions of years. So that would be pi times 10 to the minus 14 per second. Okay, so that's giving you an idea of geologic strain rates. So typical geologic strain rates, for example, isostatic uplift, what happens when you take a big ice sheet off of the land and the land rises, or orogenies, mountain buildings, or earthquake displacements, they are typically on the order of 10 to the minus 12 to 10 to the minus 15 per second, right? Very slow strain rates are more like 10 to the minus 15. Very fast geologic strain rates are more like 10 to the minus 12. So here's one way to think about it in terms of plate tectonics. A 1,000 kilometer plate straining at 10 to the minus 15 per second deforms at 1,000 times a million millimeters times pi times 10 to the 7 times 10 to the minus 15. That is about 30 millimeters per year. That's about a plate motion, right? So that's telling you something about plate tectonic strain rates. It's on the order of 10 to the minus 15 per second. Clint's got a question
for you.
Yes.
Question for you, which is, I forgot, why does the number pi enter into it? It should be obvious to me, I'm sure.
No, there's no logic for it. It's just sort of a coincidence. It's not exactly pi, but it just simplifies these calculations if you don't have to remember a number.
Huh.
It's just a little geological oddity or geophysical oddity or whatever you want to call it. Now we get into something that is very confusing to me still, and that is the constitutive equation, which you'll hear from time to time. And this is the mathematical relationship between strain rate and stress for ductile flow. And for nonlinear rheologies, it has this form, which is the strain rate is equal to some constant times the stress to some exponent, which is typically between 1 to 5 for most rocks, to e to the minus exponent minus E over RT, where E is the activation energy, which describes the minimum energy necessary for creep to start in crystals, which values on the order of that. And then R is the gas constant, and T is the temperature in Kelvin. So you can rewrite this in terms of stress, right? So that stress is equal to that constant times the strain rate. And you can substitute known values of the constant, the stress exponent, and the activation energy. And this allows us to mathematically compare the strength of different rock types under ductile deformation. And here we see them. So these are a wide range of rocks that have been studied in the laboratory: albite rock, northosite, clinoperoxide, and then down there at the bottom, rock salt, which is especially interesting because it's so much different than everything else. It's got a much lower activation energy. The stress exponent is significantly higher, and that constant is negatively. So we all know that rock salt is weak. So that, and you won't have to know this for the midterm, don't worry. This is just kind of cool stuff that is useful to have heard about at some point. All right, so here we've got laboratory experiments of rock deformation. On the left, undeformed. On the next one, we've got a low confining pressure. So we're seeing a lot of failure, fracture. And then on the right, high confining pressure. So we're seeing ductile deformation there, as we would expect. And we can plot curves of stress versus strain and see that. So these are the same things: differential stress on the y-axis and strain in percent on the x-axis. And this is for various limestones and marbles. At constant pressure and temperature, but variable strain rate, rocks are weak. At low strain rates, rocks are weak. At constant temperature and variable pressure, rocks are weak at low pressure. You can see that that fracture limit is at a much lower strain rate for low pressures than for high pressures. And rocks are weak at high temperatures. So these are the same rocks, and depending on the environmental conditions you put them under, they'll behave quite differently. So here we've got creep strength versus depth for a wide range of things. So on the far upper left, that's rock salt. No surprise, that's very weak. Very small difference in strain, very weak. And on the other hand, the thing that's strongest is olivine, right? That is circled there. And you can see quartz is sort of halfway between olivine and rock salt. All rocks get weaker as temperature increases. And remember, the mantle is rich in olivine, which is a strong mineral, and the continental crust is rich in quartz, which is a much weaker. So we can take from this that rocks will creep or flow more with greater depth because of higher temperature. That an olivine-dominated rheology mantle is stronger than a quartz-dominated rheology, the continental crust. And because the oceanic crust, which is doesn't have any olivine, any quartz in it, but it's kind of intermediate. That dB in this curve is a pretty good equivalent of oceanic crust. So continental crust would be weaker than oceanic crust, would be weaker than the mantle. Okay, so we're going to remind you of the Byerly's law here. So Byerly's law, looking at depth, strength of rocks, just following Byerly's law, right? Rocks get stronger and stronger and stronger. And if this was what was controlling the strength of Earth's interior, plate tectonics would be impossible. There's no way that there could be plates that move, but it's not. So if we combine this curve, which shows depth versus rock strength under the ductile regime, with this one, which shows the rock strength as a function of confining pressure, we get this. This is the strength, a sort of a typical strength profile for the Earth down to about 80 kilometers depth. So in all cases, the lithosphere will fail by the weakest available mode at any depth. You know, near the surface, we're relatively warm, so it's going to be Byerly's law that controls rock strength. And at depth, where it's hot, it's going to be these ductile laws, the constitutive equation that's going to determine the strength of the rocks. And you end up with something like this. This would be the strength of sort of a typical rock as a function of depth. Stronger and stronger down to about 40 kilometers, then gets really, really weak fast. Yeah. Hello, hey, Walter, how you doing? You got a question?
Yeah, this shows the brittle domain going down to 40 kilometers, but
Yes.
usually the brittle is only down to 20.
Well, this is not really a real rock, or this is just to develop the intuition of what controls rock strength. It's this intersection between, Byerly's law and the constitutive equation, brittle, shallow, and ductile deep. But yes, this is not a very good example of the Earth, but the general relations are good, right? If a student understands the general shape of this, then they can understand that point of maximum strength is going to go up or down depending on a number of factors, right?
Right. Just as a comment, we don't generally see many earthquakes below 20 kilometers because it's warm and ductile.
Yes.
The curve looks a little bit more, there's more detail to the curve.
Yes, and this kind of understanding really informs our understanding of why earthquakes, for the most part, are limited to the uppermost 20 or so kilometers of the Earth. It's because of this. Earthquakes are in the brittle domain, and once we get into the ductile domain, there are no earthquakes.
I can give you an example where we get plenty of earthquakes in the ductile domain.
Okay, well, let's not confuse the class yet.
All right.
Let's wait until they're slightly less confused about these. I mean,
All
I
right.
know they're confused because when I first started seeing these, I was confused. And it takes you a while to get your brain around it. I know this, and what I'm trying to do
fair enough.
is build their intuition, help them build their intuition about rock strength, which is what I think is one of the most challenging concepts in tectonics. Maybe why it's not in the book. Yes, Clint.
Yeah, one thing you haven't mentioned, but you've mentioned in previous lectures is the World Trade Center analogy.
Oh, yes. Okay. Yes, this is an interesting point because it's very everybody cares. There was a conspiracy theory that steel melts at I forget what the number was, but that the temperature of burning jet fuel doesn't reach that temperature. Therefore, it could not have been the jet explosion and burning fuel alone that caused the towers to collapse. But this took this conspiracy explanation was offered in ignorance of the understanding that rocks lose strength rapidly before they melt. And that applies to steel too. So we mentioned the homologous temperature, which is about 50% of the melting temperature. Up to the homologous temperature, the material has pretty much all of its strength. But at temperatures higher than the homologous temperature, higher than about half the melting temperature, the strength falls away very, very rapidly until there's absolutely no strength at the melting temperature, of course. And that's what was responsible for the failure of the towers. It wasn't, the steel was heated up enough that it lost the structural integrity it had when it was cold. Good point. Okay, so let's look at oceanic lithosphere. So oceanic lithosphere is pretty simple. There's no quartz in the in oceanic crust, either in the pillow basalts or the sheeted dikes or the gabbros. So it completely follows the brittle domain down until the strength of olivine in the ductile domain, as determined by the constitutive equation, takes over. So this is a typical strength profile for oceanic lithosphere. So oceanic crust, as you may recall, is maybe 6 or 7 kilometers thick up here. So the rest of this is in the upper mantle. So this is telling you something about the lithosphere. So the lithosphere in oceanic, for this profile, the base of the lithosphere is on the order, is basically where the rocks have no strength, so very close to 80 kilometers or so. Now, these diagrams will be different depending on heat flow, which determines the temperature structure, and for the strain rate, but this is a typical strain rate of 10 to the minus 14 per second, and the heat flow fairly low, 42 milliwatts per meter squared. So we've already said that. I don't think we need to spend any more time because we're getting a little bit short on time. Now, continental crust, on the other hand, looks more like a jelly sandwich. So here we've got, you know, a quartz dominated rheology strength, brittle for this far and going down. And then at the moho, the olivine takes over. And Walter's got another question. Go ahead, Walter.
Very briefly, go back one. Oceanic crust is olivine dominated.
Relative to quartz, yes. We've got a very simple rheology we're discussing. We're discussing olivine dominated and quartz dominated only. Yes, it's more complicated.
Oh, I just meant that there isn't much olivine in the crust.
You know, in the oceanic crust, there is some olivine. You know, we can argue about this, but I've already made the point that diabase is a useful analogy, you know, and it's definitely stronger than the quartz dominated rheology.
Okay.
So this is kind of what the continental crust looks like. Now, this is a very useful jelly sandwich, right? Because it makes you understand, when I first started thinking about collisions and why structures were where they were, it was a little confusing. But if you understand that the thicker the continental crust is, the weaker it is. Once you understand from this diagram that the thickness of the continental crust doesn't mean thicker continental crust is stronger. In fact, just the opposite, that thicker continental crust is going to have higher temperatures at depth and therefore will be weaker. Then this diagram, you start to understand a lot of things very good. So just to reiterate the jelly sandwich model for lithospheric strength, here we see, you know, the brittle upper crust, the ductile lower crust, and the brittle upper mantle. All right. Now, this is an interesting diagram. This is sort of we're showing three things here: stable shield or cratons, which have low heat flow, generally speaking. Then we have Paleozoic crust, which have higher heat flow. And then we have regions of high extension, like the Rhine-Graben or the Basin Range. And these have much higher heat flow. And because of these relationships, where we enter into regions of greater weakness or less strength with the hotter we get, this is telling us that these regions of high heat flow are necessarily going to be the regions that are deforming. We know that cratons are strong. We've talked about them being strong, and this is the reason they're strong, because they have low heat flow. So Byerlee's curve extends to greater depth. So here is a number of strength profiles. These are slightly more complicated, aren't they? So differential stress in megapascals, right? Here we're seeing Byerlee's curve going down to there. We're looking at 67 milliwatts per meter squared. These are Cenozoic and Mesozoic rifts. And here's an Archean craton. And what you can see for these strength profiles both going down 100 kilometers deep, is the rifts, all of that strength that they have is in the upper crust, and there's almost no strength below that. Whereas for Archean craton, there's strength at several levels in the upper crust, in the middle and lower crust, and in the upper mantle. So we see cumulative strength profiles like that. So warm lithosphere, these are regions that will have measurable deformation as a rule. Shield areas, very cold lithosphere, these are rigid. So here we start to see the effects of the strength profiles on extension. These are all extensional modes, and we're going to talk about different styles of rifting. Here's a narrow rift mode, here's a wide rift mode, and here's a core complex mode. We haven't talked about core complexes yet, but we will. And these are strength profiles. These are temperature profiles. These are strength profiles. And well, let's not worry about that. But what you can see here, it takes you 40 some kilometers to get to 1200 degrees. Here it takes you 90 some kilometers to get to that. So that strength profile is going to look like that for this region. And that rift is going to be very localized, going to be a narrow rift. In contrast, something with very high heat flow, it's going to have almost no strength, so it's easy to pull it apart. You're going to have a very wide rift. It's showing a core complex. So these different heat flow regimes imply different jelly sandwiches that lead to very different styles of deformation. Okay, now, as Walter alluded to, earthquake distributions are extremely useful and in defining what this zone of brittle deformation is. And here we're seeing several profiles. One is the Zagros of Iran, one is the Aegean of west of Turkey, one is Africa, and the other is the Tian Shan of Asia, near the Himalayan collision zone. So earthquakes are basically telling you about the brittle or upper deformation regime. No earthquakes. It's not telling you that there's no deformation. It's just telling you there's no failure. It's a ductile regime. So again, hot areas like the Aegean, where there's young crust undergoing extension, shows very few earthquakes deeper than 15 kilometers, whereas colder areas like Africa show deeper earthquakes. So you can use earthquake depths to sort of map where you are relative to the brittle ductile transition. So just reemphasize the importance of temperature. We can talk about MOHO temperatures. So MOHO temperatures of 500 degrees are being contrasted here with MOHO temperatures of 700 degrees, right? One is obviously the one with 500 degrees has lower heat flow than the one with 700 degrees. So MOHO temperatures of 500 degrees imply that most lithospheric strength is in the upper mantle, the blue curve here. So that could even allow for mantle earthquakes to occur. And MOHO temperatures of 700 degrees imply that most of the strength resides in the upper crust, and the overall strength is much lower. And this is going to be very important when we get to chapter 7. So we can do lots of things. Water is important. Dry upper mantle is stronger than dry lower crust. So here we're looking at olivine. And olivine can absorb a certain amount of water into its mineral lattice, but if it does that, it's going to become much weaker. So you could imagine that the mantle over subduction zones where there's a lot of water coming out is very weak, as opposed to the mantle underneath craton regions where it's relatively dry. So in this case, this is undried granulite, and this is dry diabase. So there can be different amounts of strength, and we expect that the upper mantle beneath convergent plate margins can be very weak compared to that in other parts of the lithosphere. But wet upper mantle is dry upper mantle is stronger than dry lower crust, but wet upper mantle is weaker than wet lower crust at the same temperature. So now Jackson sort of looked at this and said, well, this jelly sandwich model sounds good, but if you look at this, it's complicated. So here we've got the same temperature profile. And in the one on the left, we've got wet lower crust and dry upper mantle. You can see all the strength in the upper mantle, the green. And the one in the middle is dry lower crust and wet upper mantle. And there you see the strength is in the, a lot of strength in the lower crust that you didn't see on the left. And then here we've got wet lower crust and wet upper mantle, and there's almost no strength in either the mantle or the lower crust. So they're all three of these are jelly sandwiches, but the strength resides at very different depths. So as you can imagine, the story I'm telling you gets very, very complicated very quickly. And this is another lecture that could easily turn into an entire course, if not a series of courses. Fortunately, you're not signed up for that. Okay, now what about the creme brulee model for lithospheric strength, right? So, jelly sandwiches are all well and good, but if you're really going out on the town, you're going to want a creme brulee. Okay, what is a creme brulee? Well, you beat 6 egg yolks, 4 tablespoons of sugar, a half a teaspoon of vanilla extract, beat until creamy, mix in 2.5 cups of hot, heavy cream, bake in the oven at 375 Fahrenheit, then put into the refrigerator to chill, add 2 teaspoons of sugar to the top and broil until the top is crisp. Okay, now that crisp upper top is clearly following Byerly's law, whereas the material underneath it is following the constitutive equation. So there was an article that entitled "The Long-Term Strength of Continental Lithosphere, Jelly Sandwich or Creme Brulee." And so up atop, you're seeing the creme brulee model where there's no strength below the upper crust. And below that is the jelly sandwich model where there is strength. And their argument was there's almost no single strength profile that characterizes all continental lithosphere, and that the creme brulee model may apply to some specific settings, such as basin and range or the Western US, but the jelly sandwich is more widely applicable. So I'm going to leave you there with that. It's time, and absolutely, if I could end more of my lectures talking about tasty desserts, believe you me, I would. But that you got that for one. I guess maybe that will make up for the fact that I had to subject you to a fairly complicated and confusing lecture about rheology and brittle and ductile deformation. But I hope you have a feel for this really interesting field